We're going to be continuing with the truck shipment example that was covered for one-time shipments, but instead of solving that operational decision where we're deciding between truckload versus LTL for a particular size shipment, here we're going to look at a more tactical decision where we have knowledge of annual demand for shipping a product, and then our problem is to determine what is the best shipment size, taking into account all of the relevant cost factors beyond just the actual charge for a shipment. We're going to be continuing with the same set of data from the previous problem. So instead of having to open up that script, I'm just going to recreate the relevant data from questions 1 through 7 from the one-time shipment example using the January 2018 provisional PPI values. So I basically created the two structures, the shipment and the truck structure, and then the maximum payload remains as a variable, likewise for the PPI values. And then for question 11, given that the demand for the product is going to be 20 tons per year, what would be the number of full truckloads required? And for that, we can basically just take the annual demand divided by the shipment size to get the shipment frequency. And here we end up with a value of 3.2727. And the reason that the number should not be rounded is that the choice of a year to represent annual demand is entirely arbitrary, and our results should carry over if we switch the time period. For question number 12, what is the shipment interval? Well, that's just 1 over the frequency. And then the number of days per shipment, we can multiply the interval in years by 365.25. Since we're not restricting it for a particular year, that may or may not be a leap year. So since 3/4 of the years are not leap years and only 1 out of 4 is, we can use 0.25 to keep all of the accuracy. For question number 13, what is the annual full truckload transportation cost? The full truckload transportation cost, we can calculate it on a dollar per ton mile basis. So for question 13, we can convert it to right around 42 cents per ton mile. And then from that, we can calculate the overall charge as 44.53 using our current data with updated PPI value as compared to the slides, which may have a different PPI value. We can also calculate it using the original transport rate in the truck structure, which is on a dollar per mile basis, as opposed to the rate for full truckload, which was specified as a dollar per ton mile. In this case, we were multiplying tons times dollar per ton mile times distance, so everything had canceled except for dollars. Here we have the number of truckload shipments, so we can think of this rate as the dollars per truckload mile, and then times the distance in mile. So in that case, it's an alternate way of getting the same value. And then finally, the third way is using the matlog function, where it's called transcharge, and we provide 3 input values. If we wanted to do the charge for less than truckload, then we would provide a 4th input argument, which would be the PPI value for less than truckload. And then if we kept the truck structure, the transcharge would give us which is the lower of the 2 charges. If we wanted just the LTL, then we would leave this 3rd argument empty and only provide the PPI value. By not providing the 4th argument, we're saying that we just want to consider truckload shipments. So I'm multiplying that times n, the frequency, and I get the same calculation a 3rd way. For the second part of this question, we're given an interval constraint that the shipments have to be done at least every 3 months. So that maximum time is 0.25 years. So we can revise the rate to represent the facts and on a dollar per ton mile basis, and we get this result. Or another way of looking at it is we can take 1 over that restriction and basically say that we have to have at least 4 shipments per year. And with that, we can then recalculate. So in both cases, we get the increase in transport cost associated with that shipment interval constraint. For question 14, we're given enough information that we can calculate the additional data needed to be able to estimate the inventory cost for this product. In particular, the alpha value is equal to 1 because we have constant production and constant demand. So that results in an alpha value equal to 1. The value of the shipment on a dollar per ton basis is equal to $25,000. And then the inventory carrying rate of 0.3 is derived from the fact that the product loses 5% of its value after 3 months, which, using the average values for interest or funds together with average warehousing cost, then is approximately 0.3, where the main factor, essentially almost 20% of the inventory carrying cost is the obsolescence factor. So with that, we can then calculate the overall inventory cost for shipping full truckloads, and that's equal to over $45,000. Then for question 15, we're going to be looking at the principal measure that we'll be using to evaluate freight transportation alternatives, and that's the notion of total logistics cost, which in this example is just the sum of transport charges plus the cycle inventory cost. Other types of inventory, pipeline and safety stock, could also be added to total logistics cost. Also, we could look at differences in purchase cost for product if it's sourced from different locations. It's not necessarily true that it can always be purchased for the same price. So since there's differences in price at different locations, that's, in that case, would then be something that is relevant for making location decisions or logistics decisions. So in that case, it should be part of the total logistics cost in this calculation. So for question 15, we can then add up our transport cost and our inventory cost to get an overall cost. So this was done doing it sort of element by element. But since this is such a common thing that we'll be using to do different types of evaluation, within MATLAG itself, there is a function for total logistics cost called TOT, log cost. And the first input argument is the size of the shipment. In this case, it's just the max payload. And then the second argument is the transportation charge for that size shipment. So we again use the same Qmax value. And then the third input argument is the shipment structure. So with that, we can get results. In this case, the function returns as a first output argument the total logistics cost, and then as a second the transport cost, and then as a third the inventory cost component. So if we do want those second and third output values, then we can catch those when it's returned from the function. For question 16, here we're trying to, instead of shipping full truckloads, determine, given that we're going to be shipping independent point-to-point truckloads, would it be better, given the inventory cost considerations, to maybe ship less than that? Well, we can solve it as essentially a EOQ type calculation, where we have an approximate formula that's just the square root of the different terms, and we end up with a value of about 1.9 tons. That same calculation, again, because it's such a common thing, there is a MATLAG function called min TLC. And just like with the trans charge, if we specify, in addition to the shipment structure, just the truck structure, then we get the truckload total logistics cost. There's also an option of specifying a third input argument, which would be the PPI for less than truckload. And just like with the trans charge, it would give us then the min TLC for less than truckload, assuming that for the second input argument, we left that blank. If we provide both the truck structure and the PPI for LTL, then the min TLC will give us the minimum total logistics cost for truckload or for LTL. So with that, we can calculate this, and then first value returned is the total logistics cost, and then the second value returned is the optimal quantity. The reason that it returns the total logistics cost as the first output argument is that if we want to use that as an objective to actually minimize based on other factors, then it's convenient to have total logistics cost be the first output argument from min TLC. We can also calculate it given that we know now what the optimal size is. So in this case, we determine using the function what is the optimal size. Now that we have that optimal size, and say we didn't know the total logistics cost, this would occur in cases where instead of using the formula to get an optimal size, if we were just told that, instead of 1.9 being optimal, what if we wanted to ship 1 ton? What would be the total logistics cost of that? Well, in this case, we don't want to use this function because it determines the optimal. We can't pass it any particular size. It gives us just the optimal size. So in that case, we can kind of go one level below and look inside and use a function that then directly calculates the total logistics cost. And in this case, the transportation charge is also calculated using a MATLAB function for trans charge. So we're using these two functions together to get the total logistics cost. And inside of the min TLC function, both of these functions are in fact called. But this is if in situations where we have a particular shipment size that's not the optimal truckload, and we want to determine what is the total logistics cost. So when we can do that, we can solve it and get the results in terms of total logistics cost. If we look at the totals, we get the same as returned by min TLC. One nice thing here is we also get the breakdown of the transport and the inventory cost components. And as is always the case for optimal truckload, the transport and the inventory are always equal to each other at optimality. And for this particular one, instead of using the formula, we could get the same optimal result by calling fmin search and then passing this as a function handle to the optimization. In this case, it's not really necessary to do this search because we have an analytical formula that gives us an optimal. And as we'll see with less than truckload, when we try to combine both less than truckload and truckload, there are actually two separate minima. And by using just fmin search by itself, it would be highly dependent on what we pick as a starting point. In this case, we picked just the max payload as a starting point because for the truckload shipments, it has a single minimum. It's sort of like the single facility location problem. It doesn't really matter where we start, we still get optimal. But that is not the case when we are considering truckload and less than truckload. So in general, this is not a good approach for solving this. For question 16, we also may be interested in looking at, instead of shipping as an independent point-to-point truckload, since if you think the max payload was 6.11 tons, in terms of minimizing our total logistics costs, we should actually be shipping less than 2 tons. And to do that, we get a significant reduction in our total logistics cost, almost half. But then can we actually do better than that? So instead of having, what we're saying here is we're going to be shipping a truck that is only 1/3 utilizing its available capacity. So two-thirds of the truck shipped as an independent point-to-point truckload would be empty. Instead, it's maybe a better thing to do something other than point-to-point. Any other type of multi-stop truckload shipment may give us a cheaper cost. So in this case, we could either within our firm or hiring a carrier take advantage of the fact that you could maybe do multiple pickups and or multiple deliveries, combining it with our load, and then utilize more of the truck's capacity. In terms of the best case scenario would be that with all these other shipments, the truck's capacity is fully utilized. So in essence, we would be having our shipment shipped as a portion of a full truckload shipment. So in that case, we could look at what is the full truckload equivalent cost. So we can calculate that, and for that we can use the dollar per ton mile basis, where the maximum full truckload quantity for our particular product is Qmax. And in that case, we would end up with a transport cost as one of the allocated full truckload component shipments of this much. And then we can do the same for the inventory. Here the inventory is going to, again, still be the optimal truckload size. We could put both of these together and then use the MATLAB function variable display to look at the results. And in this case, the inventory cost stays the same. So there's no change in inventory cost because we're still shipping QTL as a quantity. But in this case, since we're shipping as part of a full truckload, the best case or lower bound on our transport cost goes down to over just a little bit over $4,000. So that's a very significant reduction in transport cost. In reality, we would probably never be able to exactly realize that. One reason would be that the other shipments that we would be combining with would have different densities. So the combination might not be as cheap as we're estimating based just on our product. But also there are, it's unlikely that a truck can be exactly fully utilized. There's also some additional deadheading if it needs to travel in terms of multi-shipments. So the total distance might be greater as compared to a independent point-to-point shipment. So for all those reasons, we're not likely to exactly realize this, but somewhere in the middle, maybe halfway between independent versus full truckload, or maybe a third of the way, would be something that would be likely in practice. So in general, you never want to ship a truck that is 2/3 empty. That's not a good long-term strategy to be profitable. And what it's telling you is that in this example, that we should not be shipping as independent point-to-point truckload. We should really be looking at other alternatives, either sharing the truck via hiring a carrier that has other customers, or potentially using LTL. And we'd want to consider those as additional alternatives for this particular problem. For question number 17, we are going to in fact look at what would happen if we are going to be shipping it as LTL. And for this example, there's no analytical formula. So in this case, we either have to use fmin search ourselves, or we can just use the option of using min TLC, where we leave second truck structure empty, specify just the PPI for less than truckload. We can calculate, or we can use the total logistics cost function as an alternate. And then display all of this information. In this case, the min TLC function returns the total logistics cost and the quantity of the shipment, and then that value is then used inside of the total logistics cost function to allow us to break out the transport cost and the inventory cost components separately. And when we do that, you can see that in the case of less than truckload, there's a big reduction in cycle inventory because we're shipping a much smaller quantity, less than 1 ton of the product, but there's a significant increase in the transport cost component. Overall, the cost is $40,000 as compared to under $30,000 for truckload. So less than truckload, or LTL, is not the better alternative. Here also that the shipments themselves are going to be every 14 days as compared to the much longer interval for truckload shipments. So there's a big difference in terms of LTL versus shipping it as truckload. There's a side issue that's important when dealing with LTL, and that's selecting the optimal starting point. So one reason that it's advantageous to use the min TLC function is that it tries to pick a starting point that it knows is feasible for LTL. So if you used min search using just the total logistics cost for LTL and tried to solve that, you can end up with solutions that are not going to be feasible. So what this cell here does is just illustrate that phenomena. So here I'm going to define a function handle for less than truckload. And then I'm going to use our standard approach. In this case, I'm going to pick a starting point equal to Qmax. And when I do that, when I pick that as my starting point and then solve, I end up with infinity as a result, and I need to increase the maximum number of iterations. The reason for that is that Qmax is greater than the 5-ton limit. So in terms of getting a LTL rate, if I pass it a shipment size greater than 5 tons, the formula returns infinity as the rate. Basically, and the reason for that is that the data generated or used to generate the estimation formula did not include values in that range, so it would not be valid to use the formula to extrapolate from the formula to values within this range, because it's really not data that was used to create the value. So it's giving you infinity, so the fmin search is basically just spinning its wheels and not able to solve. So instead of that, you might think, let me just take my truckload size. That's less than 5 tons. It's only 1.9 tons as a starting point. And if I do that, I basically get the same thing. I'm getting infinity as a result. And the reason in that case is actually to do with the cubic volume. If I take the 1.9 tons and convert it into what would be the total cubic volume, it's over 850 cubic feet of volume. And for the LTL shipments, they have to be less than 650 cubic feet. Anything greater than that is not feasible. And again, it returns infinity because there were no shipments used to generate the empirical estimation regression formula that had volumes greater than 650. And if you went to a website and tried to get a quote for an LTL shipment of something of this size, it would return back that we don't ship product of this volume. You should probably look at doing some type of truckload shipment. So this would be the case of doing maybe a multi-stop shipment. It's probably not the case that you'd want to go all the way to independent point to point, but you'd want to contact a carrier and combine maybe with other shipments and ship a much larger quantity than would be feasible for shipping it as LTL. You could think of LTL as just being sort of like UPS or FedEx for a couple pallets. But once you get more than a couple pallets, you probably want to consider other types of truckload shipments greater than LTL. So that is what this is actually telling you. Another example, if we set our starting point at 0 and then solved, here we get a result, but the result is just equal to 0. And the reason is that the size of the shipment, 0, is less than the minimum size of 150 pounds. And again, the reason is the same, that there was no data for LTL shipments for shipping anything less than 150. If you tried to ship something less than 150 pounds, and if you went to like a website, FedEx, for their LTL shipment and put in a value less than 150, they would likely either flag it as being invalid or more likely redirect you to their Package Express service, which doesn't allow shipments greater than 150 pounds. Actually, companies like UPS, they have a limit of 70 pounds as a maximum shipment size. There, the 70 pounds is the maximum that a person can carry without using a small hand truck. So UPS restricts everything to 70 pounds. But there are other services that allow shipments within the range of 70 up to 150 pounds. But for LTL, it basically starts at 150 pounds and goes all the way up to 5 tons as the range of shipment sizes that are valid. So with these two considerations, we can define an upper bound of 650. What is the corresponding quantity? We can also do 150 pounds in tons. And then we can take the geometric mean as our starting point. And we know that in this case, it's going to be feasible. So when we solve it using fmin search, we get this result. And that is essentially what the min TLC function is doing in terms of solving for this problem. If we look back up, we can see that, and you can see when we solved it using fmin search, we got 0.7694, which is the same value that we got right here. So picking a starting point is an important issue, but in our case, it's taken care of inside of the min TLC function. For question 18, how should the product be shipped? For that one, we can just call min TLC with both the truck and the PPI value, so it's going to take the best of the two. And in this case, we can return a third argument that will then tell us as a logical variable whether LTL or truckload was selected for this. And we do this, we get 0, so it basically false, so it's not LTL, it was shipped truckload. The corresponding trans charge for that shipment size is that, and then we can get the same TLC value that was returned by the min TLC, the same 2858, and then we can use vDisplay to see these results, and saying that we have shipments every just under 35 days between shipments. And since we're shipping at truckload, transport and inventory costs are exactly equal to each other. This tells us that it's truckload versus LTL. This is the independent shipment transport charge, size of the shipment, and the total logistics cost. Then if we want to plot this, we get this, and this is what I was mentioning about having two different minima. In this case, I don't know if it's exactly a minima, but it's an inflection point. And then here we have a minima. So in this case, we're in the range of truckload being feasible. A problem could arise, though, if we picked a starting point here and we're using fmin search, we would end up with this value. So the solution used by min TLC when solving a problem like this is to solve the less than truckload, find its optimal size, and then solve truckload, find its optimal size and corresponding total logistics cost, and then pick the minimum of the two. So it's essentially solving two separate problems as opposed to one combined objective function to avoid the two local minima problem. And then for question 19, we're basically going to change our value for our product. So instead of $25,000 per ton, it's going to be $85,000. And as you can expect, when we make that change, we rerun the same analysis, and now the product is being shipped as a LTL. And in this case, we're spending a lot more on transport as opposed to inventory, and we're getting the lowest possible total logistics cost for this scenario. Also, the product is being shipped much more frequently, every 5 days. We can plot this result. Here we get the same two minima, and here you can see that the LTL is the lower of the two. The next question is a situation where we add a second product to the mix. And the second product, what we know about the product is that the product is a class 60 product. So that class 60 product corresponds to a density of 32.16 pounds per cubic foot. The value is 5 tons. And we're going to assume it's the same carrying rate. So what we can do is call a function in MATLAB called vec_destruct, and it's a nice way of combining, adding additional shipments to a shipment structure. What we're doing here is we're taking the first shipment structure for our first product, and then what vec_destruct does is, given that we specify existing shipment structure as a first argument, then it basically adds, in this case, another element to a structure array that's created. And that structure array is going to have a F field value of 80, corresponding to the number of ton demand for the second product. Then this is its density and its value. And for the other values, the alpha and the H and the distance, since we're assuming all of those to be the same, we don't have to re-specify them. It just uses the same values for those fields unspecified that were defined in the original first shipment argument. So we can create our second shipment structure. If we want to see what it overall looks like, we can use the sDisplay function. S is for structure display. And what structure display does is it uses the field names as the column headings in this result. So we can see it has the same distance, same alpha, same H, and then different V different S and different F values. So with that combined shipment structure of two elements, if we look over here, we can see that SH is now a 1 by 2 array of structures. So it's a 2-element structure array. We can pass that 2-element structure array to the min TLC function. And what it does is it returns two separate values. It basically minimizes the total logistics cost for each shipment separately. We can then calculate the shipment intervals. And here, since we're using an array of two values, we have to put the F field values in square brackets and use the dot divide since we're dividing by a 2-element. This by itself is 20 and 80. So it's a 2-element row vector. And then we can look at vDisplay. And here I've done an option where I've specified this argument as true. And what that does is it takes each column reported and reports the sum value. So in this case, I'm summing up both of my total logistics cost for each shipment, assuming that they're shipped optimally. In the case of the first shipment, it's shipped LTL. Second one is shipped truckload. These are the different intervals, and this is my total logistics cost. So this basically sets the stage for question 21. And question 21 is that since they're starting and ending at the same origin destination, it would make sense that these could be combined onto the same truckload. In this case, it could even be two shipments that are the same company, or it could be somebody located close by in Raleigh and delivering to somewhere close by in Gainesville. Typically that's the job of the carrier, to find candidate shipments that have similar origin destinations that are good candidates to be combined into multi-shipments. In that case, you can start to approach some of the cost savings associated with shipping it as an allocated truckload as opposed to an independent point-to-point truckload. So for this, all of these steps of doing the aggregate shipment are all embedded inside of a function called AggShip. And I can pass it a single argument, which is my 2-element shipment structure array. And what I get then is a single structure that has the elements of the corresponding aggregate. So now I have 14.3, which is the aggregate density. I get the sum of the 20 and 80 demands in tons. Alpha just passes through. For the value, I get a weighted average, weighted based on the demands, and then H passes through. So now with that aggregate, I can essentially look at 3 different shipments, 1 and 2 separately, and then the third shipment here is actually the aggregate shipment. So this is a nice way of seeing. And you can, when you do an aggregation like this, you should see the values somewhere in the range of the corresponding shipments that you're aggregating together. So in this case, 21,000 is between 85 and 5. If it was greater or less than those values, then something's wrong in the aggregation. Likewise for the density, looking for a value somewhere in the middle of the elements used to compose it. In this case, the F's are just added together. So with that, we can then treat this as a single shipment, call fmin search, and then report the results. We get 58,000, and that compares to the almost 74,000 before. Finally, we can take all of this and use the mDisplay function to provide a little bit nicer way of displaying our results of this analysis. What I'm doing is I'm creating a matrix of values, M, and I'm using the fact that within MATLAB, if I provide, or actually within this mDisplay function, if an element of a matrix array has a not a number, NaN, in it, it just leaves it blank in the displayed table. So it's a nice way of including empty values within a display. And the best way to look at it is to just execute all of this. And you can see this summarizes all of the results. So these are shipments 1 and 2 by themselves. Here, if we ship them as 2 separate independent, we got this total logistics cost. When we shipped them as an aggregate, we got a reduction in total logistics cost.